In this video lesson, we're going to be doing the first part of 8th grade geometry standard number 1, or 8.G.1. Our learning target is I can rotate, reflect, and translate geometric shapes and their parts. We've got quite a bit of vocabulary, so remember the best thing about a video lesson is you can pause at any point so that you can write down information you see on the screen. Make sure you've got all of your definitions written down. So to get started, we're going to talk about those 3 words that I listed in our I can statement. The first one being translate. Translate in math means a translation, which is a rigid motion transformation that slides each point of a figure the same distance and direction. Now, a rigid motion transformation is a transformation that preserves the size and shape of the figure. You're going to see the words rigid motion transformation in all 3 of the definitions on this page. So for translate, we're taking a shape and we are sliding it 3 units to the left, 4 units up. And we'll use some more technical vocabulary like vertical and horizontal instead of left, right, up, and down. Our second definition is reflect. A reflection is a rigid motion transformation that flips a figure across a line of reflection. So there's those words again. Rigid motion transformation means we're going to end up with the same size and shape. And the key word here for reflect is flip, that the object is going to be flipping over. And our last definition here on this page is for rotate. A rotation is a rigid motion transformation that spins or turns a figure. So we see rigid motion again. That means it's going to end up being the same size and shape. And this time we will be rotating around a fixed point, which is called the center of rotation. And we're going to be given an angle, for example, 90 degrees or 270 degrees. And we're actually also going to be told a direction. Are we rotating clockwise or counterclockwise? We're going to talk about each one of these 3 in more depth in just a moment. But before we do, I want to talk about rigid motions and how they produce shapes that have the same size and shape. And of course we have a fancy math word or a scholarly word, a word that means figures that have the same size and shape, and that word is congruent. This is the symbol for congruent, and all 3 of these transformations, translate, rotate, and reflect, all produce congruent figures. So if I take this red check mark and I slide it over here, that's a translation, it's congruent. These 2 red checks are congruent to one another. They are the same size and they are the same shape. They're both check marks and they're exactly the same size. If I do a rotation, if I spin this in any amount of degrees, clockwise or counterclockwise, these 2 objects are congruent because they are the same size and they are the same shape. They are still check marks. That's the shape, and you can see that they have not changed sizes. I can also take this, this original shape and I can reflect it or flip it. I've actually got the choice here in my menu. It even says the word flip. I can flip it in this direction. Now this is a reflection. It looks like a mirror image. And as you can see, they are still the same shape, still check marks, and they're the same size. So this symbol, the congruent symbol, actually has 2 parts to it. And I want to talk about this bottom part first. The bottom part here is actually an equal symbol. So if I cover that up, you probably notice that that right there is an equal symbol. And that's because congruent means that I'm going to have the same size and same shape. So the equals part of our definition of congruent appears right here in the symbol. The second part of our symbol is this top part, this curvy line. And we will talk a lot more about that symbol in a later lesson. But this is the symbol for the word similar. Now, similar, when we're talking about geometry, means that 2 objects are the same shape, but not necessarily the same size. So right now, these 2 red check marks are congruent. They're the same shape, both check marks. and they're the same size. If I were to make this this check mark bigger or smaller, they are now similar. They're the same shape, but now they are different sizes. And again, we will talk about similar a lot more in a later lesson. So when we are doing translate, rotate, or reflect, all are rigid motions which preserve size and shape, we are going to end up with two figures, and they're congruent to one another. They're the same shape and same size. If I move this star, I'm sliding it. That's an example of a translation. We can translate objects in any plane, but in 8th grade math, a lot of times we are going to see translation happening on a coordinate plane specifically. So here are two more vocabulary words, and these two words are words that I get mixed up all the time. And that is the word image and pre-image. Now in this example, I can see that this is the original shape. I can tell that this is the original shape because there is an arrow pointing to the new shape. So I have an original shape and I have a new shape. They're both the same shape. They're both right triangles, and they're the same size. All that has happened is that I have moved this triangle. Now, our scholarly words for original shape and new shape are pre-image and image. And this is where I often make a mistake. Now, pre means before. So the original image is the pre-image. And when I think about it like that, when I take the time to label which is the original and which is the new, then I don't make a mistake with this. But it's really tempting for me to call the original shape the image. But in fact, it's the new shape that we refer to as the image. This is really confusing for me. I have to slow myself down. I have to label them. Here's my original shape, here's my new shape. And when I take the time to do that, then I don't make that error. I know the original is what happened before. I know that that should be the pre-image. So for a translation, we've got our image sliding, and each point of the figure is moving in the same distance and the same direction. So in this example, if I take a look at this point right here that I'll mark with a red dot, and I find the corresponding dot point on my new shape, I should be able to count how far this has moved. It looks like it has moved 1, 2, 3, 4 units to the left. So for this translation, I could say that I translated my shape 4 units to the left. And if I checked on all of the other points, for example, this point up here on the top, which I'll mark with purple, I should be able to move 4 units to the left from here, and I should be on my corresponding spot. 2, 3, 4, and in fact it is. And I'll check the final point of my triangle. 1, 2, 3, 4, and there it is. So in fact, every point on this shape has moved 4 units to the left, not just the 3 points that I have marked. I could mark any point along this triangle, every single one of these little tiny dots that I'm making, any of these dots over here, every single one has translated or has been slid over 4 units to the left. Now we're going to write an even better description of 4 units to the left. We know that left-right movement here, horizontal movement on the x-axis, horizontally, left or right, I'm going to use that word instead. I'm going to say that I have translated this shape 4 units horizontally. Now, horizontally could mean left and it could mean right. So I have to think about, is this a positive 4 units or is this a negative 4 units? On our coordinate plane, left and right, moving to the right is considered positive movement, Moving to the left is considered negative movement. So since I am moving my shape to the left, I know that this is negative horizontal movement. So I can't just leave this statement how it is now, move 4 units horizontally. That implies that I'm moving to the right. I need to say that this has moved negative 4 units horizontally. This lets me know that my shape is moving to the left. Now on our next example, we're talking about reflections. Reflections, our keyword is flip. So if I take this shape here, and again, I can choose, it even says right here, flip, it doesn't say reflection. I can choose to flip my shape in that direction. I can choose to flip my shape in another direction. Oftentimes you will see shapes being flipped or reflected either over the y-axis or over the x-axis. But in fact, you can you can reflect over any line, any vertical line, any horizontal line, any slanted line. So here's how a reflection is done. A reflection occurs over a line of reflection. That line of reflection has to be exactly in the middle of your 2 shapes. So in this example, I was not told what the line of reflection is, but I can see that there is a line that is exactly in the middle of these 2 shapes, and it happens to be this line, which is the y-axis. So if I was describing this reflection, I would say that I reflected over the y-axis. And if I wanted to be even more specific than the y-axis and give the y-axis an equation, I would say that I reflected over the line x equals 0, because that is the equation for the y-axis. That's 2 different ways to say the same thing. If I was told to take this original image, what was the word for original image? You gotta slow down and think about it. The original image is called the pre-image, which means that this over here is my new image, which is called image. That's that part I always get confused by. If I was asked to perform this reflection, if I did not see this dashed triangle over here, here's the process for doing a reflection. You're going to take a point and you are going to find how far it is from your line of reflection. In this case, this point right here is 2 units away from the line of reflection. That means my new point that corresponds to this will also be 2 units away, just on the other side. So if this is 2 units, then this will also be 2 units. We're going to add in some more vocabulary here. I'm going to go ahead and name this triangle, triangle A, B, C. Here's another clue for if you are doing problems and you have to create a new shape. When you do this, I can't call my new point point A because I already have a point A. So the correct notation is to now call this A prime. The prime marker is a little line, almost looks like maybe an apostrophe or an exponent of 1. It is read as the word prime, and it lets me know that something has been done to my original shape. My original point A has become A prime. This lets me know one transformation has happened. Let's go ahead and let's go ahead and reflect point C. Point C is also 2 units away from my line of reflection. Therefore, my new point C, 1, 2, will also be 2 units away, just on the other side. I would like to call this point C. However, it is my new point C, so I will call it C prime. That lets me know C has transformed. It is now over here. It is C prime. And I can do the same thing with my final corner of my triangle, which is point B. Point B is 1, 2, 3, 4 units away from my line of reflection. My new point B will also be 1, 2, 3, 4 units away. And I can't call it point B, I will call it B prime. So another clue when deciding if something is an image or a pre-image is to take a look at the notation. If it has regular letters, triangle ABC, that's your original, that's going to be your pre-image. If it has prime markings, that's going to let you know that a transformation has been done to the original shape. Our last rigid motion transformation is a rotation. Rotations require the most amount of information in order to be able to perform this transformation. I need a center point. I need an angle of rotation, for example, 90 degrees, 120 degrees, and I also need a direction. Now, when I say direction, I'm referring to clockwise or counterclockwise. In this example, I have a heart shape, and if I click on my heart shape and begin to spin it, it will rotate either clockwise or counterclockwise. And it's going to rotate around its center point. I can drag this heart shape clockwise, which is the direction a clock spins, the hands of a clock, or counterclockwise, which is the opposite of the way that a clock moves. The same thing will happen with our triangles on the coordinate plane. Now in this example, you can see that this was triangle ABC, and it has been labeled for us. This is our pre-image, which lets me know that this over here is the image. Something has happened to this shape that has landed it over here on this side of my screen. The notation A prime, B prime, and C prime also is another clue that lets me know something has happened. Now, to do a rotation, we will talk a lot more about this in class, but the idea is this. If I draw a hook from the center of rotation, and by hook I mean how did I move horizontally, how did I move vertically? If I draw a hook that looks like this, 2 units to the horizontal, 1 unit vertically, if I rotate this hook, I will land on my new point that corresponds to this. Now this is point B. Here is my new point B. If I draw a hook here, I will see that it is also a distance of 2 and a distance of 1. So it's the same size as the first hook that I drew, but I can see that this original hook has been rotated. So let's talk about the direction that it got rotated. It rotated from here to here. That is counterclockwise. So I can tell that this is counterclockwise, and I can also tell that this is 90 degrees. My original hook went from laying down on its side to standing up. So I would call this a 90 degrees rotation around the origin. 90 degrees counterclockwise around the origin. I'm going to be a little bit more specific here, and I'm going to write the coordinates of the origin, which is 0, 0. We can rotate around any point. It's just that it is often that we will be rotating around the origin. We'll be rotating around 0, 0. I could do that same process for any of these points, and I would find the same thing happening with every hook that I drew. If I drew a hook here from the origin over to point C, I see that my hook is 4 units and 1 unit. And if I draw a hook to C prime, I see that it is also 4 units and 1 unit. It's just that the hook has been rotated 90 degrees around the origin in a counterclockwise direction. So the final thing that we need to discuss is congruency statements. In this example, I have 2 quadrilaterals, and I would need some more information. Most likely, I would be told that shape ABCD is congruent to shape RSTU. The order of the letters is very important. I could not write RSTU in any other order, because then I would not have the correct angles corresponding to the correct angles, and I would not have the correct sides corresponding to the correct sides. So down here we have a definition for your notes. If two figures are congruent, then all corresponding sides and all corresponding angles will have the same measure. So I can tell just by looking at my list that angle A will be the same size as angle R. Whatever this measurement is will be the same as this measurement. And the same is true all the way down the list. That means that angle B will correspond to angle S, angle C will correspond to angle T, and angle D will correspond to angle U. So we're actually going to be writing 4 congruency statements for our angles. And instead of calling it angle A, we are going to name it with its full name, which uses the 3 letters that make this angle. In order to make angle A over here, I actually need these 3 letters, D to A to B. And so here's what it will look like. Angle D, A, B is congruent to angle. Now, here's what I love about a letter list. I can follow the letter list, or I could go directly to my shape. I'm going to start with the letter list, and then I will confirm on the shape. I just said angle DAB. D, A, B. I'm going to do those same letters, except using this list. Since I said D first, I have to say U first. Angle U. So I said DAB, URS. It's going to be the same as angle URS. Let's check to see if that worked. If I trace D to A to B, does that look the same as what I've written here? U to R to S. Absolutely. In fact, it's capturing that angle that I had marked in purple before I even started. I will have 4 of these statements for the angles. This was only the first one. I'm going to erase my markings. I'm going to erase the markings from my letter list so I don't get confused. I'm going to do one more of the angles before moving on to an example of the lines, and you can finish the rest on your own. If I wanted to talk about angle B, I can see that angle B corresponds in the letter list to angle S. These 2 angles will have the same measurement. But I'm not going to just call this angle B, I'm going to name the entire angle A, B, C. So I will write angle A, B, C is congruent to, well, I'm going to go back to my letter list. A, B, C corresponds to these letters, R, S, T. So I will write congruent to angle R, S, T. I'm going to check again to see if it worked out. A, B, C, that's this blue angle here in the corner. And I'm going to check what I wrote here, R, S, T, R, S, T. There are 2 more angles that need to be named and write congruent statements for. I would like you to please finish that in your notes. There are also going to be 4 corresponding sides. I'm only going to do 2 of them. You can do the other 2 independently. The process is going to be exactly the same. The only thing that will be different will be our notation, because we're not talking about angles anymore, we're talking about a line segment. The way that we mark a line segment is by writing the 2 letters that we need for the side, and then putting a line segment symbol on the top. So I will go ahead and start with line segment AB, or side AB, which is written like this. AB with a line segment on top. Now that is going to be congruent to, well, let me go over here to my letter list. AB corresponds to RS. So I will write RS with the line segment symbol on the top. AB is congruent to RS. Okay? If I come now on my picture and mark RS, I can see that those do appear to be the same length. And since I have my statement here telling me that it's congruent, I can confirm that that is the same length. I'm going to do one more, and I'd like you to finish the last two on your own. The last one I'm going to do is the hardest one. It's this side over here. Okay, I can call this either line segment AD or DA. And here's why it's challenging the first few times you do it. In my letter list, the letters are not side by side. So if I choose to call this line segment AD, I can write line segment AD is congruent to. In my other list, I did A, so I have to start with R in my other list, and D, which corresponds to U. So I have to say that line segment AD or side AD is congruent to side RU. Now I did that for my letter list. Let's go to the shape itself to figure out if we're talking about the same side. And in fact, we are. I can see that it's in the same location connecting to my other side. And that's how I can use a letter list to write congruency statements about corresponding sides or corresponding angles. Please make sure that you finish all 4 congruency statements for your corresponding sides and all 4 congruency statements for your corresponding angles.